Hi everyone, my name is Pfohl. Today I'll be talking to you about our paper titled Net Benefit, Calibration, Threshold Selection, and Training Objectives for Algorithmic Fairness in Healthcare. As a disclosure, this work was completed during the course of my time as a PhD student at Stanford, but I've since completed my PhD and served as a research scientist at Google. To guide the presentation, I'll consider a few key questions. First, I'll focus on how we might come to a set of best practices regarding conducting practical algorithmic fairness assessments for the purposes of evaluating predictive models in healthcare. In that context, I'll discuss how decision-making, or rather the context of decision-making in which the model is used informs the operationalization of algorithmic fairness principles. Second, I'll consider related questions concerning best practices for model development. In that context, I'll consider whether model training objectives should include explicit fairness constraints, as well as the question of how we can build models that predict outcomes well for each patient population. So to summarize some key takeaways and recommendations, first off, it's important to transparently document all protocols regarding dataset preparation, cohort construction, and model development, as well as any assumptions implicit in the problem formulation, which includes those related to the intended stakeholders and their values in the intervention and its effectiveness, as well as the relationship between unmeasured constructs and their operationalizations via measurable proxies. For model development, it turns out that maximizing net benefit for each population generally coincides with learning the best fitting set of models that are calibrated at the relevant thresholds for each population. Training one model with empirical risk minimization over the entire population appears to work well for this goal, especially after accounting for any miscalibration. For evaluation, it's important to report a variety of performance metrics and to contextualize these metrics in terms of the properties of the intervention in order to understand model performance holistically. For fairness, we find that calibration-based assessments are generally more useful than those that assess differences in true positive or false positive error rates. This is because in the case that the outcome instance differs, such differences are present in cases when the outcome ascertainment is unbiased and decisions are made on the basis of a calibrated score to confer maximal net benefit for each population. However, in cases where such differences point to unexpected differences in incidence, this could potentially help alert for potential measurement biases. Furthermore, it's important to not over-rely on any assessment of fairness as a sole indicator of whether machine learning-enabled intervention is equity-promoting or introduces harm, but rather the results should be used to motivate any further refitting, recalibration, data collection, or sensitivity analysis, or revisiting of the problem formulation. Finally, current approaches to algorithmic fairness are relatively limited in scope, but can still be useful for model reporting or auditing. It's important to remember that current approaches do not readily enable detection and mitigation of upstream biases, nor enable reasoning over the effects of model-guided interventions on health outcomes or on the mechanisms that contribute to health disparities. As such, machine learning-guided systems and policies that are apparently fair can still introduce and perpetuate harms, just as those that are apparently unfair may not be inherently harmful. An important future direction in this space is to develop formal approaches to integrate knowledge or assumptions regarding the broader system that a model is deployed within into all stages of the data science workflow, from the earliest stages of problem formulation to the evaluation of deployed systems.